Thank you. On December 10th, 1985, in the Stockholm City Hall, I received the Nobel Prize from the hands of His Majesty King Carl Gustaf of Sweden. I shared this prize with my partner, Dr. Joseph Goldstein, and we received the prize in physiology or medicine. In this talk, I wanted to tell you some of the steps that we took to earn this prize. And I think if some of you follow these 9 simple steps, you too may someday be on the concert hall stage in Stockholm. The first step is to be curious. My curiosity began when I was 13 years old and I got my amateur radio operating license. And a friend of mine and I used to build transmitters and receivers, mostly from kits. And I would plug them into the wall, usually when I finished about 3 a.m., and I would promptly blow every fuse in the house. And my parents were not very happy. But that's where the curiosity part came in, because I had to go back over everything I had done and check every circuit and find the wire that I had soldered into the wrong place. And that type of curiosity, that type of retrospective problem solving is something that I still do today. It's at the core of any experimental scientific field. The second step is to train with a Nobel Prize winner or the equivalent. I grew up in Philadelphia. I graduated from the University of Pennsylvania undergraduate college and the University of Pennsylvania Medical School. And then I went to Boston to do an internship and residency at the Massachusetts General Hospital, one of the Harvard hospitals in Boston. And after that, I went to the National Institutes of Health, just outside of Washington, to do a research fellowship. And there I came under the spell of a man named Earl Stadtman. Stadtman was the leading biochemist at the National Institutes of Health. He was a brilliant scientist and a very critical man, and somebody from whom I learned how to think like a scientist. It's quite surprising how many Nobel Prize winners actually trained with Nobel Prize winners or the equivalent. I say the equivalent because Stadtman didn't receive a Nobel Prize, but he did receive the National Medal of Science, which is the equivalent in the United States. The third step is to find a partner to share the adventure. So I met Joe Goldstein in 1966 when we were both beginning interns at the Massachusetts General Hospital. We had different backgrounds. I had grown up in Philadelphia, one of the nation's largest cities, and I went to the University of Pennsylvania School of Medicine, the nation's oldest medical school. Joe grew up in Kingstree, South Carolina, a town of 3,000 people. I used to think Kingstree was in the middle of nowhere, and I visited it, and I realized the middle of nowhere is a defined place. It's the middle of nowhere. Kingstree is off to the side of the middle of nowhere, somewhere. But Joe grew up there, and then he went to medical school here in Dallas at what was then known as Southwestern Medical College. And somehow he got accepted as an intern at the Massachusetts General Hospital. And the minute we met, we bonded. And the reason was because both of us were interested in the very basis of disease, the scientific basis of disease. As interns and residents, our first job was to diagnose our patients and institute the appropriate therapy. But when that was done, we used to meet in the doctor's dining room late at night and talk about the underlying causes of our patient's disease. Why does this woman have rheumatoid arthritis? Why does this man have a heart attack? And it was that shared interest in the basis of medicine, the scientific underpinnings of medicine, that brought Joe and me together. And then it just by chance, it happened that both of us were accepted to do fellowships at the National Institutes of Health. And there we found a problem that fascinated us. This little girl, this is not our patient, for true honesty. We didn't have a camera. But our patient had the same disease as this little girl. The disease is called Familial Hypercholesterolemia, or FH. Our patient was 6 years old. She was hospitalized at the NIH because she was having heart attacks. The coronary arteries that carry blood to the heart muscle were being occluded by deposits of cholesterol. Now, we usually see this problem in 60-year-old men, and here was a 6-year-old girl who couldn't walk across the room without having the crushing chest pain that comes from poor circulation to the heart. We knew it was genetic because she had a brother who had the same condition. And we knew it had nothing to do with diet because we put her and her brother on a totally cholesterol-free diet for 6 months. While they were in the hospital, they ate nothing but vegetables and fruits. And still, their cholesterol level remained elevated. The reason that she was having all these problems is because her blood cholesterol level was 10 times above normal. And when that cholesterol is so high, it forms these deposits in the arteries and blocks the arteries. And when it's so high, if you notice her knees, when she falls down and bruises her knees, there's so much cholesterol in her blood that it gets out into the tissue and forms these big bumps, which is a hallmark of this disease called familial hypercholesterolemia, which I will now refer to as FH. This little girl had the homozygous form of the disease, the most severe form. She inherited 2 abnormal genes, one from each parent. But of course, we had no idea what those genes were. Fortunately, this homozygous condition is very rare. Only 1 in a million children has this condition. But when they have it, they have this enormously high cholesterol and this incessant, progressive coronary artery disease. Now, the reason that her cholesterol level was so high was because she had an increased number of these cholesterol-carrying proteins in her blood. This is low-density lipoprotein, or LDL. LDL particles are spherical particles about the size of a small virus, and each LDL particle carries 1,500 molecules of cholesterol. And LDL is secreted into the bloodstream, and it circulates in the blood. Her cholesterol was elevated because the number of LDL particles in her plasma was 10 times above normal. Each milliliter of her plasma contained 10 times more LDL particles than normal. And LDL is sometimes referred to as the bad cholesterol because it has a tendency to stick to the arteries and block the arteries and produce heart attacks. These are the coronary, this is a human heart, and you can see the coronary arteries. These are the arteries that carry blood to the heart muscle. And when LDL is elevated, eventually it deposits and blocks these arteries, and the heart muscle that is counting on these arteries for its blood supply, that heart muscle dies, and that causes the crushing chest pain of a heart attack. So having seen these 2 children, the brother and the sister, and having been very frustrated that there was very little one could do in terms of therapy, Joe and I decided that we would try to solve 2 puzzles. First, what controls the level of LDL in the blood? No one had any idea. And secondly, what mutation disrupts this control in familial hypercholesterolemia? Now, Joe had been a medical student here in Dallas, and he had promised his professor that after he did his training and in Boston and at the NIH, he would return here to Southwestern to start a program in medical genetics. So he was already committed to coming back to Dallas, and he tried to convince me that I should move to Dallas, and together we would work on this problem of familial hypercholesterolemia. It wasn't so hard to convince me because the medical school here in Dallas was outstanding, and it would have been a great triumph to join that faculty. Now, it was a different story with my wife, Alice. Alice grew up in New York. We were both total Northeasterners. In fact, when we worked at the NIH in Bethesda, Maryland, we thought that was the Deep South. So coming to Dallas wasn't a high on Alice's priority list, but I give her eternal credit because she agreed to come with me to Dallas, and of course I promised her it would only be for 1 year. And that was 43 years ago, and we're still happily married, and we've raised 2 talented Texas daughters. Now the next step is to find someone to pay for your work. And in Dallas, we've been very fortunate to have several donors, 2 of which are anonymously depicted here, who have been strong financial supporters for many, many years. And of course, we got a great deal of money from Uncle Sam in the form of federal grants. So now we had a problem to work on. We had a place to work on it. We had money to do the studies, and the next question was work very hard. And I can tell you that Joe and I did work very hard. We were doing clinical work at the same time as we were running our laboratory, and that made it even more difficult. But I can attest to the many, many hours that we spent. And this is true of any scientific problem. If you're engaged to solve a scientific puzzle, you have to be totally consumed by it. It has to become something that you can never stop thinking about, day or night. It has to be constantly on your mind. You have to be constantly figuring out what the next experiment should be and what went wrong with the last experiment. And it requires that level of commitment, and we were able to do that commitment. Of course, I was able to do that commitment because Alice shared the major burden of raising our 2 daughters. So we have the money, we're working very hard, we had to solve the problem. Our approach was to take cells from these patients and cells from normal subjects, grow them in petri dishes in tissue culture, and measure the way that they handled cholesterol. And what we found was that cells in the tissue culture, human cells in tissue culture, first of all, they require cholesterol. Every cell in the body requires cholesterol because it's part of the building block of the plasma membrane that surrounds the cell. And cells have 2 sources of cholesterol. It was long known that cells could synthesize cholesterol, as shown on the right side of this slide. They synthesize it from a simple building block called acetyl-CoA. It takes a series of 30 different enzymatic steps to assemble the complex cholesterol molecule. And one of the important enzymes that you'll hear about later is called HMG-CoA reductase. That's an early enzyme in the cholesterol biosynthetic pathway. This pathway had been worked out over the previous 3 decades by brilliant biochemists, several of whom received Nobel Prizes. But what we found that was new was that cells have another source of cholesterol, that the cells could actually use the cholesterol contained in the LDL particle. And in order to use the cholesterol from LDL, the cells produced a protein, which we call the LDL receptor, that goes to the surface of the cell, and it binds LDL as it moves past the cell in the circulation. And the receptor binds the LDL particle like a first baseman catching a ball from a shortstop. And once the LDL binds to that receptor, it gets taken into the cell and then delivered to a digestive organelle where the whole lipoprotein particle is degraded. The protein component and all the lipids are degraded, and the cholesterol is liberated so that it can now be used by the cell to make new membranes. Now, this process is subject to feedback regulation. When the cell is in need of cholesterol, cells produce more LDL receptors. And when cells have too much cholesterol, there's a feedback mechanism that cuts down the production of LDL receptors. And that's what that arrow, that dashed arrow at the bottom means. When cholesterol accumulates, the number of LDL receptors goes down. This will be important later in the talk. Now, what was the problem in FH? The problem is at the very first step. Children with homozygous FH have mutations in both copies of the gene for the LDL receptor. And as a result, their cells cannot produce LDL receptors. The cells can't use LDL as a source of cholesterol. They survive in tissue culture because they are able to synthesize their own cholesterol, but the LDL remains outside the cell in the culture medium. Now, how does this work in the body? Well, in the body, the majority of LDL receptors are in the liver, and the liver uses LDL receptors to filter out LDL from the circulation and remove the LDL particles so that the LDL level stays low. So as shown here on the left, a normal liver cell has a certain number of LDL receptors, and it's able to remove LDL at a rapid rate, and as a result, under normal conditions, the LDL level is low. But as shown on the right, in FH, the liver cells cannot produce LDL receptors, and as a result, LDL accumulates to enormous levels in plasma, eventually depositing in arteries and producing the heart attacks that we've been discussing. Now, the next step is essential to any successful scientific career. Don't let anyone tell you it's not true. You have to be lucky. And in our case, the greatest stroke of luck came from this man, a man named Akira Endo, who worked at the Sankyo drug company in Tokyo, Japan. In the 1970s, when Joe and I were working out the LDL receptor story, Akira Endo was screening fungal extracts to see if he could find a natural molecule that would block cholesterol production. And Endo was able to find such a molecule. And the way that this molecule worked was to inhibit the enzyme HMG-CoA reductase. Endo's discovery was the first in what is now a larger class of drugs called statins. And the way the statins work is that they are specific inhibitors of this enzyme HMG-CoA reductase, so they block cholesterol synthesis. Now, when Joe and I heard about Endo's discovery, we immediately contacted him and we started a collaboration, because we had the idea that if we could block cholesterol synthesis in cells, then the cells would be deficient in cholesterol and they would produce more LDL receptors in order to get more cholesterol. And indeed, we were able to show, both in tissue culture and in experimental animals, that when the cells were exposed to these statin drugs, cholesterol synthesis was blocked and the inhibition of LDL receptor production was blocked, and so the cells made more LDL receptors. Now, I want to turn now from FH to the question of why it is that heart attacks are the most frequent cause of death in the United States and other industrialized countries. If we all have normal LDL receptors, why is it that the LDL level in so many of us is high enough to produce heart attacks, not at age 6, but at age 60? And the reason is shown on this slide. Again, when people are eating a low-fat diet, a vegetarian diet, a diet that doesn't have very much dairy products or meat in it, the liver cholesterol level is low, and the only cholesterol that's really in the liver is cholesterol that's synthesized there by the pathway that I showed you. But when we eat high-fat diets, those diets are very rich in cholesterol. The cholesterol is absorbed in the intestine and delivered immediately to the liver. And over time, it expands the pool of cholesterol within the liver cell. And when that happens, the cell says, I have enough cholesterol, and it activates this feedback mechanism which turns down the production of LDL receptors. It doesn't turn them off completely, or we would all look like these FH children. But it turns them off partially, and it's enough to raise our LDL levels from a physiologic normal level up to a level that makes us vulnerable to heart attacks. Now, we reasoned that since we eat these high-fat diets, and we have two sources of cholesterol in our liver cell, we reasoned that the statin drugs could inhibit the cholesterol synthesis part, and even if we were continuing to eat these diets, there would be a relative reduction in cholesterol in the liver cells, and LDL receptors would be increased, and the plasma LDL level would fall. Again, we showed that first in experimental animals, and then it was shown in people. And we worked together with the Merck company to help them develop the first statin drug that was introduced commercially in 1987. Now, this slide shows the effect of statins on coronary heart disease or heart attacks. And this is a meta-analysis of studies of multiple clinical trials on different statins that were done in the decade shown here. And altogether, they involved over 67,000 subjects. They were studied for an average of 5.1 years. All of the subjects were at high risk for heart attacks. Half of them were put on a cholesterol-lowering drug, and half of them, a statin drug, and half of them were put on placebo. And the statins reduced the plasma LDL level on average by 28%, and there was a 31% reduction in heart attacks. Now, this meta-analysis was done in 2003, but since then there have been many, many more studies. Now, well over 100,000 patients have been studied, and the results are always consistent. In every one of these trials, reducing the LDL level with statins reduces heart attacks. Statins are now taken by more than 20 million people every day worldwide. And so the work that began with this child, this 1 in a million children with this rare genetic disease, eventually led to a treatment that is now being used to treat the bulk of the population that is predisposed to heart attacks. Now I want to get to the final step, and this is by far the most important. None of the other steps matters if you make a mistake on this final step, the most important step of all. I'm only half facetious here. As a professor in a medical school for the last 40 years, and as one of the directors of our MD PhD program, I've seen a lot of brilliant, potential brilliant physician scientists of both genders, men or women. And some of them have to terminate their careers because their spouse doesn't understand the purpose and why they're working so hard. And why aren't we taking a vacation this year? And why did you miss the soccer game for your child or the piano recital? It's really important in my case that I formed two important partnerships. One with Joe Goldstein, by the way, both of which are continuing to this day. One with Joe Goldstein and the other with Alice. And I think both of them were critically important. All right, that's my story. And 9 steps. Now go out there and be curious and make discoveries. Thank you very much.